Juniors, is these last chapters that we're going to do are largely recapping some ideas from Algebra 2 last year with some minor extensions here and there. So should be pretty familiar topics, which is good, right? Like, we've done all this new stuff and some of it was pretty hard. It's nice that the end of the semester maybe is circling back and seeing some stuff that's pretty familiar. This chapter 15 is dealing with exponential, logistic, and logarithmic functions. Now, we talked last year about exponential and logarithmic functions already in your Algebra 2 class. Logistic will be new, but they're not a big deal. We'll look at some some applications of these types of functions that we didn't get to in Algebra 2 class, and maybe go a little bit deeper with some of these things, but it's not, not so bad. Should be relatively familiar. You guys ready to hit it? Let's do it. All right. We're starting talking about exponential functions. So exponential functions are of the form a times b to the x, where a is not 0, b is greater than 0, and b is not equal to 1. So let's take a moment. Why don't we want to let a be 0? What would happen if a is 0? You'd have just f of x equals 0. That's a constant function, not an exponential function. So that's that. Why do we not want b to be 1? One to any power is 1, so you'd have a times 1, so you just have like the function y equals a. Again, that's a constant function, not exponential. Why do we not want b to be, why do we have to have b to be positive? What would happen if b was negative? Well, remember here, where's the variable at in this exponential function? It's in the exponent, right? Everybody agree? That's where the x is. So the exponent can be any number, right? Specifically, it could be things like a half, or a fourth, or a sixth, or an eighth, or a tenth. Why is that a problem if b is negative? What's an exponent of 1/2 the same as? A square root. And why would square rooting a negative be a problem? You get an imaginary result, right? So this function, if we let the value for b be negative, would have all kinds of discontinuity all over this thing every time you ran into an exponent that had an even denominator. Woof! That's a big mess, right? We don't want to include something like that. That's not going to behave like an exponential function. Everybody cool with that? A little bit of vocab here. The value for a, we call the initial value. And the reason we do that is if we say, okay, what's f of 0? We know that anything other than 0 to the 0 power is 1. So the initial value, like if x equals 0 is the initial, and we get a when we do f of 0. Everybody's okay with that? And again, as we kind of go through stuff, we'll be hitting some of these exponent properties from last year, and I'll just kind of write those in as the side as we go. Hopefully you still kind of remember those, but we'll review them as we go. The b we refer to as the base for the exponential. So there's that. Just as an aside, 0 to the 0 is? Nope. Nope. It's indeterminate. Means that it could have many different values. Amongst those, you could consider it, I think, both positive and negative infinities. But if you just said undefined, that would be okay. Anything other than 0 to the 0 is 1. But 0 to the 0 is a meh, meh. Okay? Cool. All exponentials have a key feature. They all have a horizontal asymptote. For the form above, that horizontal asymptote will be at y equals 0. All right, let's just run through a couple of computational examples, mostly as a good excuse to review some properties of exponents. So if I have negative 2 times 4 to the x, can I write that as negative 8 to the x? No. No, very bad. So the rule for multiplying, if you have two things with the same exponent, you can multiply the bases together and keep the exponent the same. Or if you have two things with the same base, you can multiply them together and by adding their exponents and keeping the base the same. But if you have two things that have different bases and different exponents, you cannot multiply them together. Just as an aside. Common mistake that I see students make, worth recapping, since it's like directly related to exponent rules. That again, we remember from last year, you just needed to be reminded. You know what I mean? Because stuff fades. If it didn't, I'd be out of a job, right? There's a joke. Anyways, so if I wanted to do f of 2, what do I want to do? Plug 2 in for x. So I have negative 2 times 4 squared. What do I do first? Exponent. So I get negative 32. What if I wanted to do f of 0? Fast! Negative 2. Great. How'd you do it so fast? Yeah, it's just the initial value, right? Cool. Very good. What if we did f of -3? How do I deal with that negative exponent? Anybody remember? Yeah, it makes a reciprocal. So that becomes 1 over 4 to the third. So again, x to the negative a is 1 over x to the a, provided x is not 0. Why can't x be 0? Oh, did I drop the negative? Thanks, Mackenzie. Is that what you're going to say?
Yeah.
Yeah, sure. Get that in there. Everybody doing good? Ringing some bells? Maybe. What do I do if I want to do 4 to the 1/2? Yeah, that's a square root. So again, our rule there is the nth root of x is equal to x to the 1 over n. And let's do one more. What am I going to do with that? Well, this is the way you'd want to think about it. Three over 2 is the same thing as -3 times 1/2. And we know that the exponent of an exponent we multiply, so I can use that property kind of in reverse. Circle that one too, I suppose. How's that? It's all right? It's all right. Let's do another kind of example. Oh, I did table below, didn't table below me. Make that a little bigger, I suppose. Oh, Boise. Okay, that's good enough. Come on now. Stop being a booger. Okay. Table below gives the values for an exponential function g of x. Find the equation of that function. So what we're asking, or we're being asked to do, is to write the equation g of x equals a times b to the x. Everybody cool with that? So we need to figure out the values for a and b. There's a hard way to do this and an easy way to do it. Depends on the points that you're given. The point that you need for it to go the easy way is the x equal to 0. Why is that the easy way? Yeah, that's exactly right. Gives us the a square away, which is lovely. Now I can use any of the other points. My suggestion would be to use the point with the x-coordinate 1. I can then plug that in for x and g of x to solve for b. And then we're all donezos. So we know our a is 3 and our b is 5. Sweet, dude. How's that feel? It's okay? That's not so bad. But Mr. Kulik, you said there was like also a hard way this could go. Do you have an example of that? Yeah, of course I do. What do you take me for? Some kind of schlub? Don't answer that. Particularly if the answer was, yeah, Mr. Kulik, you seem like the schlubbiest schlub that ever schlubbed. You know, that's not nice. Oh, boy, is he. Missed the the. He table below doesn't make a lot of sense. Let's make that the table. All right. The table below, blah, 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 blah. Same situation as before. What don't we have, though? The x equals 0, right? So what are we going to have to do then? We're going to write a system of two equations. So I'm going to use this point. And I'm going to use that point. And that's going to form a system of two equations. I'll refer to those as equations A and equation B. If you remember back to your Algebra 2 course, what were the algebraic methods we had to solve a system of two equations? Elimination and substitution. I prefer to use elimination here. Unlike the equations that we solved using elimination last semester or last year, where the variables were added or subtracted, here the variables are being multiplied. So to eliminate the variables from this equation, instead of adding and subtracting the equations, I'm going to be dividing. So the question becomes then, should I divide, or which of the two, equation A or equation B, should be the numerator of my division problem? What I typically do is I pick the one with the smaller denominator, or the bigger denominator to be the numerator. It makes the algebra a little bit easier at the end. It saves us a little bit of a step, and I'm cool with that. Everybody happy with what I did there? Note, you could also do this via substitution, but this, I think, is a lot less messy algebraically. So 12 divided by 48 is just 1/4. The A's cancel out. And then to divide b to the negative 1 divided by b to the negative 3, I get b to the negative 1 minus 3. Using that property of exponents. Negative 1 minus a negative 3 is 2. So far, so good? You guys will holler at me if you got questions, right? How do I get rid of the squared on the b? Square root, that's good. Now, because we're doing it to both sides of an equation, we get a plus or minus, but we know b is the base of our exponential. So what do we know about b? Has to be positive, so I don't even have to worry about the minus. There's my value for b. Sweet! What am I going to do now to get a? Plug that value to b back into either equation a or b. I'm going to choose to plug it into b. What letter is this? This was H, I think. How's that feel? A little bit trickier than the previous example, but like, yeah, it's still not so bad, right? Okay. So, one of the frustrating things with dealing with exponential functions is if I have two of them and I want to compare them, the base can be different between both of them. And the base makes a big difference in terms of like the behaviors going on. So one of the things that we'll frequently want to do is to find a way to rewrite our exponential so that they all have the same base. The question becomes, okay, what number would I often use? And the answer to that is we often use the number e. We call that number the natural base, or Euler's number. So we abbreviate that with the letter E. That's equal to the limit as x approaches infinity of 1 plus 1 over x to the x, and was about 2.71828818, yada, yada, yada. This is just some irrational number. And while it seems like, whatever, okay, this thing pops up all the time in like natural situations when you might not expect it. So you do enough math and physics and you'll be like, oh, wow, the answer's E? That's weird. Wouldn't have expected that. And we'll look at when we get a little bit further in to a situation where like it becomes obvious as to where this kind of crops up naturally. Okay, so with this we can say any exponential function f of x equals a times b to the x can also be written as f of x equals a times e to the kx. Note this implies that b is equal to that e to the k. And again, just like we had before, a can't be 0 and k can't be 0. So this is just alternate ways to express the same function, right? So we have two different types of exponential functions. We have growth and decay. So if we have the classic form of our exponential function where the a is positive and the b is greater than 1, that's a growth function. And if the a is greater than 0 and the b is between 0 and 1, that's a decay version. Or if we have the natural number-based version and the a is positive and the k is positive, it's growth. And if the a is positive and the k is negative, it's decay. And then the rules are flipped if the a is negative. Everybody still doing okay? You tell me if you weren't, right? In red?
Yeah.
It's greater than.
Okay.
All right, let's look at a couple of examples here. So here's my first one that we'll look at. It says, given the population of a certain city in 1990 is 782,248 people, and the population of the same city in 2000 is 895,193 people, and assuming the population growth is exponential, in what year will the population reach 1 million people? So there's kind of two parts to this problem. In the first part, we're going to have to write our exponential function. And in the second part, we're going to have to solve that exponential function when it's equal to 1 million. Okay with that? So if I look at the part in yellow, this looks a lot like I'm given 2 points. And asked to write an exponential function for this, right? Now, if I treat it this way, I'd have to do that long solving the system thing, right? But who wants to be sneaky? I do. Here's what I'm going to do. Instead of relating the x-coordinate as a year, I'm going to relate it as a time, and I'm going to take my earliest year and relate it as time 0. And then I'll adjust my other to be time 10, since 2000 is 10 years after 1990. Why would I want to do that? If the x-coordinate is 0, that gives me the a automatically. Sweet! So to solve this thing then, let's I guess we'll write the form what I'm doing. I'm going to have 895,193 equals A, which is 782,248, times B to the 10th. So far, so good? If I'm going too fast or you need me to slow down and you just have a question, like any of that information is fine. Just holler it, shout it on out. You know. To solve for B, what should I do first? Yeah, divide by 782,248. Okay. How am I going to get that 10th off of the B? Not the square root, the 10th root. Yes, very good. And since that's an even root, technically I get a plus or minus, but do I care about that? No. Why? The base of the exponential is always positive. Just cross that out. All right, let's go to our calculator now. God bless you. And do that. So the 10th root, how do I get a 10th root? Type the number 10. I'm going to press the math button and choose option 5. That allows me to have a root of any size, particularly in this case, I picked a 10th root. And then I'll just type in my stuff. So I get that the B value here is about 101,357,8108. So my function here is 782,248 times 101,357,8108 to the x. That answers like the yellow part of my question. Right, remember we highlighted the stuff above. To answer the green part, I'm going to plug 1 million in for the output and solve for x. Actually, let's do this. Okay, so where is the variable located in this equation? In the exponent. From last year, if I wanted to solve this equation algebraically, what would I have to use? A logarithm? Have we talked about logarithms yet this year? No. Do you suppose I'm going to pull one out to use it now all of a sudden without ever having introduced it in the first place? No. What I'm going to do instead is just do this with my calculator. So what I'm going to do is I'm going to treat each side of my equation as its own separate graphing problem and then find the intersection. So to be as accurate as I possibly can, I'm going to take this entire number with me. So I'm going to store this as a variable so that I don't have to copy that whole number in. So 1 million, I'm going to type into y1, and then 782,248 times that variable I just stored, to the x. In addition to storing it as a variable, that whole number, not only do I not have to type that whole number in again to my calculator, it also stores all of the decimals that my calculator has in the memory, not just the 8 or so that it's displaying, but it has like 99, like up to 99 decimal points or something, I think, stores in the memory that it just doesn't display all of them. So I get to keep all those also when I do it that way, which is nice, a little bit of added accuracy. All right, so I'm going to reset my window now because, well, I'm pretty sure whatever window I had it set is not going to display all this stuff. So let's go back and look at our problem. So time 0 is the first time we care about, right? So the times are basically like my x's. So I'm going to put my x min at 0. So from 0 to 10, my population increased by about 100,000, right? If I go 10 to 20, I'd expect it to probably increase by about another 100,000. That's going to get me pretty close to 1,000,000. So I'm going to pick maybe 0 to 30. I want to overestimate kind of whenever possible because all I need to see is the intersection. I just don't want it to be too small and have to go back in and change the window again. So like I'm always going to kind of overestimate. Is everybody cool as to how I kind of came up with 0 to 30 there? Okay. The y's are my populations. The smallest population I care about is this 782,248. I'm not going to type that in because it's like a weird number. I'm just going to do 750,000, which is nice and round and pretty. Except I typed in 7.5 million. There we go. And then the biggest population I care about is 1,000,000. And I'm going to type something in a little bit bigger than that so I can see the intersection. So I'm going to do like 1.25 million. Yeah. Okay. Oh, I better put them in the wrong spot. Cheapers creepers. That's 750,000. That should be 125 million. And go up by, say, 100,000. Sounds good there. All right. Now let's hit graph. There's my 1,000,000 line. Here's my exponential function. There's my intersection. That's the part that I care about. How do I find the intersection on a calculator? Second, trace. Which command? Intersect. Since there's only 2 curves and 1 intersection, I can just press enter 3 times. And that intersection happens at about 18.2. But remember, what is the question actually asking us for? In what year will the population reach 1,000,000? So 18.2 isn't the year, right? Yeah, so remember this is 18.2 years after 1990, i.e. during the 2018 is when we'll reach. Oh, sorry, yeah. Sorry, my apologies. Yes. So during the 2008, during that year of 2008. Or you could say between 2008 and 2009. What? Yeah, you don't want to get into that game of like trying to talk about like a fifth of a year, because what the heck does that really mean?
Within the first.
Yeah, it's like, but what does quarter mean? Because the months are different lengths. So and is it a leap year? You don't want to play that game. We're not going to play that game. It's a yucky game. Do we feel okay with that? Now here's a question for you. We modeled this city's population using an exponential model. Do you think that's the best model we could do to describe the way a population grows? Let's take this model that we wrote, and let's say we want to find the population in, the year 2200. So that's going to be what, like 210 years later, right? So what's that say? The population of the city would be 13,284,000 and change, right? That seem reasonable to you? City going from 700,000 people to 13 million people? Why not? What are the constraints to the population of a city growing? There's a couple of good ones. There's only so much area you can build in, right? I mean, essentially, you could start building up, sure, but there's like a city's, has geographical boundaries that you have to respect. You guys agree with that? There's only so much resources that a population can consume to support those organisms, whether it be jobs or, like food or water or whatever. So most populations, rather than having a curve that looks like this, that looks exponential, let's try to draw that a little flatter at that end. We'd like something that looks like this, that has like an upper bound to it. That's what a logistic curve looks like. So logistic functions are of the form c over 1 plus a times b to the x, or f of x equals c over 1 plus a times e to the negative kx. So the nice part about these logistic functions is they have horizontal asymptotes, a lower bound at y equals 0, and an upper bound at y equals c, which more closely models what a population is going to look like, right? At some point, they're just like, can't get any more rats living on this island because there's just not enough food to support any more rats. That they start dying off as quick as they're born because they're starving to death and stuff. You get what I'm saying? It feels like this should make some intuitive sense, logical sense when you think about it, right? So there's two types of logistic functions. There's growth and decay. Some space there. So if we're looking at the one with the classical exponential in the denominator, or the one with the natural exponential in the denominator. So we say that the growth is if the b is between 0 and 1, and its decay if it's greater than 1. And this one is growth if the k is greater than 0, and decay if it's less than 0. All right. So let's first find the y-intercepts and the asymptotes, and then we'll graph these things on the calculator. I would like to do it in that order. Does that sound okay to you guys? Okay. What is the x-coordinate for y-intercept? Oh, come on. Every y-intercept has the same x-coordinate. 0! So I'm just going to do f of 0 to get the y-intercept. So 0.6 to the 0 is 1. 3 times 1 is 3. Plus 1 is 4. So I get 10/4 or 2.5. Bless you, bless you, bless you. You're welcome. The horizontal asymptotes are at always y equals 0. This is like our lower bound. And then y equals, do you remember the other one? We just wrote it down a second ago. C, which in our case is 10. That's like our upper bound, or like the limit to growth. Like our population can't exceed that. And the same idea here on the other one, right? I guess let's do one more thing before we graph these on our calculator. For part A, is that logistic growth or decay? What do we need to look at? The 0.6. Yep, so it is growth. And then How about for the other one? What do we need to look at there to tell if it's growth or decay? The what? The what? Be careful here. Notice the formula. The negative sign is part of the formula. So really what we have here is just the 2. So again, this is growth. K is equal to 2. Everybody okay? Again, I wanted to kind of hit that because it's easy to overlook the negative sign there in the formula. I'm going to graph both of these at the same time on the same window just for the sake of not having to do it twice. To type this into my calculator, I'm certainly using the fraction command because boy howdy, I would probably screw up the parentheses doing something like this without doing that. There's that. Remember how to get the E on your calculator? Second ln. The ln is just a couple buttons above the on command. We'll reset our window. 0 to 30 is probably fine, but that's a bonkers y. The y minimum here is 0 because that's the lower bound for each of them. And the biggest upper bound we have is 31, so let's do that. Go by 5s or something there too. Okay, so here we go. Here is our first one. Actually, I'm going to reset that from -10 to 10. It's not giving me a very good picture. There we go. So there's that's part A. Notice it's growth because it's increasing. And there's part B. Whoop. Notice it's increasing also. Both growths. Everybody cool? All right. Oh boy. Let's do another example. Come on. So here it says the population of a city can be modeled using the logistic growth equation given blah, 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 where P is the population in the city T years after 1950. At the beginning of what year will the city have a population of 1 million peoples? So we're asked for what year. That tells us we're going to be solving for T, right? And we're told the population of 1 million people, that's our P of T. So I'm going to be plugging that in. Does that all look okay to you guys? Again, to solve one of these things, what do you think I'm going to do? Graph it on my calculator and find the intersection. So 1 million, 1, 2, 3, 4, 5, 6 zeros. 1, 4, 2, 5, 3, 9, 7. 1 plus 2, 1.783 e to the negative 0.04982x. Okay. Next thing I need to do is choose an appropriate window to do this. Well, time 0 seems appropriate. That's going to represent the year 1950, right? And I don't know, I'm just going to guess 100 maybe. Go up to 100. If it's not good enough, I can always make my window bigger. But 100 years probably seems like a reasonable amount of time. The Y minimum, well, again, I know the minimum population the city can have is bounded by the horizontal asymptote Y equals 0. And the maximum population the city can have is bounded by the horizontal asymptote Y equals C. Now, I'm not going to type in that ugly number. I'm just going to type in 1.5 million. And we'll go by 100,000s or something. Everybody's okay with that? Let's hit graph and take a look. There's my 1 million line. Here's my logistic curve. Is it going to get that? It's going to do it. If I didn't see the intersection, what would I need to do? I have to readjust my window. That's all, you know? All right, so to get that intersection, second trace, intersect command, enter, enter, enter. So 78.86, that's not the number it was supposed to be, because I probably goofed up one of these things when I typed it in here. What did I goof up? 1.4, oh yeah, there it is. 1.425. There we go. There we go. Okay, so how would I answer this question? There's my T. What should the answer be? What would the year be? Okay, so if I add 1950, I get 2029. Because notice it takes past 2029 to get to 1 million. So at the beginning of the first year, the population's over 1 million. Won't happen until 2030. Oh, Mr. Kulik, that's so close. Couldn't I just round it to zero? No, because of the context of the question. It says very specifically the beginning of what year. If you typed in 79 in for T, you would not get a number bigger than 1 million. It'd be awful close, but it'd still be wrong. How do you guys feel? It's okay? No big deal. Nothing's super duper complicated we've done today. This looks like a good place to stop then. At this point, you guys could do up through 16. Notice the problem set isn't due until May 1st. So we're still going to do stuff that week we get back before we figure out a problem set. So there's nothing due this Sunday or the Sunday after that. Nothing else due for the seniors. Everybody's happy. You get to go on spring break and not have to worry about any math stuff, unless you choose to be worrying about your math stuff because you're like, yo, I got some stuff to catch up on. But that's on you. Okay? Great. Yes. And have a nice break if I don't get a chance to see you again.